Hello and welcome to another video. This one is about the ideal gas equation. This is the fourth video in the series about amount of substance, where I'm simply going through past papers. I don't know what this one is. I think this might be a specimen. No, it's June 16, paper 1, AQA. Up to now, we've looked at N equals CV. Now that equation, because it's got concentration and volume in it, that's for solutions. This isn't about solutions. The other equation we have is N equals M over MR. Well, we will be using that in a bit, but this is about gases and pressures and temperatures. So we need an equation with those in it. So I can't remember whether they actually give you this equation. But if they don't, it's fairly easy to remember. The important thing about this is being able to rearrange it and being able to use the right units. So obviously P stands for pressure, but it has to be in pascals, because this is really a physics equation. And physics equations use what are called base units. So instead of kilopascals, we want just pascals. Volume, we want meters cubed, not centimeters cubed or decimeters cubed. Got to be meters cubed to work in this equation. N, same as the others, moles. R is the gas constant, so we don't really have to worry about the units for that, but it's 8.31. They will give you this in the data sheet. I think it's joules. Anyway, let's just leave it at that. 8.31, I can't remember what the units are, I should do. Temperature has to be in Kelvin. It tells you there, joules per K per mole. Don't put the temperatures in degrees C, because if you do, it won't work. Right, what we need to do is find the mass of ammonia in flask Q. That's the big one. How do I know that's what they want us to do? Because that's what it says down there. I just don't want to scroll down because I want to keep all the information on the screen that we actually need. So let's rearrange the ideal gas equation for moles, because if we're going to find a mass, we're going to have to use this equation, and we need a mass. We need moles. We've got the MR because we know it's ammonia. So let's go through this. So the ideal gas equation, I'm not going to go through how you rearrange it because I spend a lot of time doing this for my A-level online students, and really we should be doing chemistry, because A-level students should really be able to rearrange these things without even having to worry about it, because this is not chemistry, this is simple maths, GCSE maths. Right, how many centimeters cubed are there in a meter cubed? We're going to have to deal with that for the volume. We're going to have to multiply that by 10 to the minus 6, because there are a million centimeters cubed in a meter cubed. The pressure is in pascals. That's no good. We need it to be in pascals, not kilopascals. So it's actually 102,000. Or you could put 10 to the minus 3 in. Sorry, 10 to the 3 in. The volume is 1 times, now it's 10 to the minus 3 times 10 to the minus 6. When you multiply indices, you simply add the indices. So 3 plus minus 6 is minus 3. So it's now 10 to the minus 3. The gas constant is what it always is, because it's a constant, and the temperature is already in Kelvin, which is very useful. Next thing is we need to work out fairly quickly what that sum comes to. So if you could work out what 102,000, well, basically we're going to divide that by 1,000, aren't we? So it's 102 on the top over 8.31 times 300. So if you could work that out, I'll work it out as well. So we'll do 102 divided by 8.31, which is that, and then we divide it by 300 as well. I get 0.0409. That is the moles of ammonia. Is that okay? What we want, what the question wants, is the mass of ammonia. N equals M over MR. Therefore, M equals, hang on. Therefore, M equals N times MR. We've got the number of moles. It's 0.0409. The MR of ammonia is obviously 17. NH3, 14 plus 3 equals 17. So we want 0.0409 times 17. Let's see what that gives us, and that should give us the volume in flask Q. So 0.0409 times 17. It says here 0.6953. Now that's grams of ammonia. So of course you can have a mass of a gas. There's no problem with that. So there's another little bit to that question. So what I'll do is I'll just pause for a moment, scroll down, and we'll complete the second bit of this question. Welcome back. I've just cleared the screen. So yes, we calculated the number of, well, the mass in grams of ammonia in flask Q. What it did say in the question was to round it up. So we'll round it up to 3 significant figures, and it was 0.695 grams of ammonia. That's what we eventually got to in the last question. Okay, so the next thing to do is to look at the rest of the question, and we will do that now. So let's have a look. We've done that. The next bit is we're going to open the tap. The temperature decreases by 5 degrees C, and the final pressure changes to 75 kilopascals. Okay, let's get our heads around that. So what's going to happen? Temp decreases 5 degrees C. What else? Tap is now open. We know the volume of flask Q, by the way. 1 times 10 to the 3. That's centimeters cubed. So what we need to do now is find out if we're going to open the tap, we've still got the same amount of ammonia. We've still got the same amount of ammonia, but now it's occupying the entire volume. So what we can do now that we've opened the tap, oh yeah, and the pressure is now 75 kilopascals. As you might expect, the pressure has dropped from what it was originally because we've opened the tap. It's sort of instinctive, isn't it, that that's what would happen. Right, so this time we're trying to find volume. Once again, rearranging, that's something you need to be able to do very quickly and accurately. We're just going to put the P down on the bottom there. So nRT over P. Just make sure the units are right. Now, if you remember, the mass of ammonia was 0.695. Okay, so we just need to turn that back to moles again. So N equals M over MR. So I can't remember what the moles was before. So it's 0.695 divided by 17, which is 0.0409. I remember it now. So that's the moles, 0.0409. Right, then we have to add the gas constant. That doesn't change. The temperature has decreased by 5 degrees. Before, it was 300. It's now 295. And the pressure, well, it tells us what that is, but it's in kilopascals. So we need to multiply that by 1,000 to get it into pascals. That will give us the volume in meters cubed. So again, I'll just pause for a moment and do that on the calculator. Okay, so I've done that sum. This works out at 0.00134 meters cubed. Right, well, this is in centimeters cubed. Maybe we want to make this into centimeters cubed as well, because we're going to find the volume of the whole system, of the other flask. Okay, so the total volume is this. But we want to put it into centimeters cubed so we can compare it with the other one. So all we do is multiply it by 10 to the 6. So we move the decimal point 6 times. 1, 2, 3, 4, 2 zeros. 1, 3, 4, 0. Centimeters cubed. This is the same as 1,000 centimeters cubed. So the volume of flask P must be 1,340 minus 1,000. That's the total volume. That's the volume of flask Q. So this is 340 centimeters cubed. So that is quite a difficult question. It's a bit unusual. Takes a bit of getting your head around. But let's just look at how many marks there are for that, because it seems like quite a lot of work. So we just scroll down a little bit. So there's 3 marks for finding that, and then there's another 3 for that. So there's 6. So obviously you wouldn't want to spend as long as I did on it, but I was trying to explain it. So you can probably do it more quickly than that. But that's how you do it. I believe that's the correct answer. Thanks for watching. If you found it useful, I would appreciate it if you'd leave a like. If you didn't enjoy it, I'm amazed you've watched it this far. But don't watch any more, because they're all going to be just like this. So if it doesn't suit your learning style, we'll go and watch something else. All right then. Well, if it does suit your learning style, I hope to see you again very soon. See you then. Bye.